lifetime. It's just wonderful.
Thanks, Scott. We're glad to be on here with you, and thank you for creating this forum for us.
Yeah.
There's us again.
All right.
And there's Ivan.
It looks like we're online.
Looks like we're on YouTubing. Okay.
All right. I might give, let's see, who were we missing? We're missing
Abby.
Missing Abby. I might give her, oh, I think she said she would be unavailable. Weren't they taking a vacation? I think that may be the case.
Okay. So I will do as much biology as I can and fake the rest of it.
I love it. You know, if you can't dazzle them with brilliance,
Bathroom with bullshit.
there you go. Well, hopefully, although we don't make any, arrogant claims to brilliance here on Sidewalk Science, we are fairly well versed in various fields of science. We have with us today on our Sidewalk Science panel, we have Dr. Ivan Phillips. And Ivan, you want to tell us a little bit about yourself for those who are just tuning in for the first time?
Yeah, I got my PhD in theoretical physics from Northwestern, where my thesis was about ways of measuring differences between matter and antimatter at colliders. So what kinds of experiments can you do to try and understand why the universe is made of matter and not antimatter, or rather, I guess it's conventional what you call them, but why there's more of one than the other.
Yeah.
Since then, I've been working in the software industry, but been very interested in philosophy and in critical thinking.
The book on critical thinking, right?
Yes, I wrote a book called Textbook Rationality, and it's about how to do the basics of rationality. It's something, and why we should be teaching it in schools.
Excellent. I love your core thesis.
In kindergarten.
There you go.
Little kids would really pick up on it.
Yeah. All right. Mike, Dr. Mike Albro, you want to tell us a little bit about yourself?
Yeah, thank you. So since Ivan mentioned his PhD thesis, I will mention mine, which was 52 years ago in 1969. And my thesis experiment was in creating K0 mesons out of gamma rays. So it's photoproduction, we call it K0s, which are a particle that's very interesting because it converts into its antiparticle. The K0 and the anti-K0 mix with each other. And that led to the discovery of what's called CP violation, which is difference between matter and antimatter.
So related to Ivan's topic then.
Yeah, related to it. That was 52 years ago. And since then I've been doing research, and still I'm doing it in my retirement as a professor at Stockholm before I came over to Fermilab, and was a little part in discovering the top quark at Fermilab and the Higgs boson at CERN. So that was all great excitement. And now I'm hoping to discover something more in my old age. So there we go. Still fun.
Yes. Science just never loses its charm, does it? All right. And then also we have Dr. John Doty. John, you want to introduce yourself?
Sure. Talking about PhDs, I have a PhD in physics from MIT. My PhD thesis was on observations of GX1+4, which is a binary pulsar near the center of our galaxy. It was a very unusual pulsar, still is, in that we think of pulsars as really good clocks. Well, GX1+4 is the worst clock in the history of pulsars. It was changing by 2% per year in its period when I was studying it. And part of what I did for my thesis research was to straighten out all the confusion about whether it was a pulsar or not and what its period was, because it had been looked at by different instruments at different times with different time resolutions. People had reported aliases. If you know what an alias is, it's where you're sampling the thing that you're looking at a frequency that's near the or less than the frequency at which it's it's oscillating, and the oscillation looks like it's on a different frequency from what it really is. And so it was tremendous confusion in the literature as to what this thing was and whether it was a pulsar at all. And I straightened all that out, and I got a PhD out of it.
Wow, that is so awesome.
So John, what is the answer? Why?
Yeah,
was
what
it...
is the answer?
Why is
it
it
a pulsar?
Oh, well, it is a pulsar. Oh, why is it changing so
Yeah.
fast?
Yeah.
Or was
Is it magic?
No, it actually fit the emerging theory of accretion torques in binary pulsars. What it's doing is it's accreting gas from a red giant companion, and that gas makes an accretion disk. And this thing must have a very large magnetic field. At least that's what fits the behavior. And so the accretion disk actually doesn't get very close to the pulsar, and it puts a tremendous, but because of that magnetic field, it puts a tremendous torque on the pulsar through the magnetic field as the gas gets trapped in the magnetic field and funneled toward the poles.
That's awesome. So we're here today with Sidewalk Science. We explore topics about science. We hope to communicate them in a way that is accessible and comprehensible to people who have a curiosity about science but don't necessarily have a professional education about it. Speaking of professional education, Joanne, you want to talk about yourself for just a second before we continue?
Sure. See, I can talk about it. I started out life as a chemist, so I actually am a scientist type person. I'm an analytical chemist, primarily in spectroscopy. So John Doty and I have a lot in common in that regard. I get tired of people not thinking, which brings me up the same thing over to Ivan. And so I began trying to teach people how to think, and got back and picked up my doctorate in the area of critical thinking. When I was picking up my doctorate, there was a confusion in the field of education that many people, in fact, the majority of people, felt that you could not teach people how to think, that you could not teach them how to think critically. And this seemed to be silly to me because we can teach people how to read and how to write. So why not how to think? And so I put up a whole series of classroom experiments. I had all sorts of wonderful things going on in which we taught people the basics of critical thinking. We taught them how to apply it to their fields, and went back in a 5-year study and demonstrated that not only did they remember how to do it, but they had put it into their personal practice throughout. So we were very pleased with that and demonstrated to the field of education that you could teach people how to think. You could teach people how to think rationally and reasonably, that they would retain it, that they would transfer it from one course area into another course area, and then into their own lives. So we made a huge change in the field of education. And this has been one of the things that I keep working on, is how do you teach science? What is the best way to get this, what most people think of as dry, dull, and boring, into the classroom and allow students to really enjoy it? Because it's fun. But that's me. I'm a silly chemist.
So, Joanne, I have a question for you. Do you know the book called Good Thinking by Guy Harrison? You
Yes.
probably do.
Yeah.
I just heard a talk he gave to the Center for Inquiry, Skeptical Inquiry, and he gave it's on YouTube. You can just check it out. He gave it last night, talked about critical thinking, and he's published a few books. And I'm going to read that one about good thinking because it sounds very interesting, and several other books like that. Yeah.
I've seen the reviews on it, and I've ordered it through Amazon or Hulu, whichever one it is. But I have not yet begun to peruse it, but it's out there.
Right, and then I'm the official co-host. Yeah.
Yes, you are.
But
I officially dub you co-host.
thank you very much. I don't have a PhD, but I have a lifetime of studying science and trying to practice thinking critically and scientifically, and being just in love with news and explanations about the way the universe works. On this program, we emphasize a scientific explanation for all that we see and all that's possible. We reject the hypothesis that it includes magic or supernatural phenomena. We also explore the intersection of humanism, which looks for the prosperity and flourishing of a human race in a responsible way and a way that respects all persons. So it's the intersection of humanism and science. We are supported in part by the American Humanist Association, as well as our local humanist group here near Chicago called the Prairie State Humanists. You can find us on meetup.com if you search for Prairie State Humanists. All right, so we're going to start our three-part program now after our introductions. I assume we have some additional viewers this week that we gathered since we presented to as a guest program to the American Humanist Association a couple weeks ago. So we start with science news, and then we have a deep dive topic, and then we'll talk about that deep dive topic. And the deep dive topic for today will be the so-called twin paradox from special relativity, as well as a more general discussion, I believe, of time dilation related to relativity. And Ivan will lead us through that in a few minutes. But first, I had a couple of interesting pieces of science news I uncovered over the past week. One was a brand new blue pigment for painting.
Yes.
First in 200 years. This blue pigment is a structural blue. A structural color is the kind of color that some reptiles and certainly most insects and many birds exhibit. That's where little plates or molecules align in a certain direction structurally in their tissue or on their skin. And the structure of those little molecules preferentially reflects or absorbs different frequencies of light. And it's the structure that gives rise to some of the more iridescent colors that we sometimes see on the breasts of hummingbirds and the scales of butterflies and whatnot. And this is a new blue pigment that's a structural color. And from what I've been reading, it's the first new way to create a blue pigment in about 200 years. And it's rare and not yet being really mass produced, so it's also very expensive, but it has some artists and others excited. And then the other piece of interesting news I saw was about some scientists who use ancient stone tools from early hominids and humans, Homo sapiens, to determine the strength of Earth's magnetic field way back when those were last exposed to flame. So a lot of times when you're making a stone tool, you can sort of anneal it, I guess, with flame, and that can reset the orientation of the molecules, and they tend to align slightly with the magnetic field of the Earth. And they can't necessarily tell from a hand axe what the direction of Earth's magnetic field was. They can do that with rocks laid down in spreading centers in ocean floors, for example. But using these hand axes and whatnot, from about 9,000 years ago or 8,000 years ago, they can determine the strength of Earth's magnetic field. And this is really instructive as we witness during the modern era a habitual weakening of Earth's magnetic field in relative terms. Some scientists speculate that the magnetic field of Earth may be getting ready to flip-flop, which it's done many, many times throughout geologic time. And this study of these tools might give them an idea of how quickly Earth's magnetic field strength recovered during from periods of weakness to periods of strength. So that's a pretty interesting study as well. Anybody else have any science news they were intrigued by this week? Mike, you're muted.
Yeah, can I just ask a question about that? And maybe John knows better, but do we have a theory for how the Earth's magnetic field flips?
I've heard all sorts of guesses, but nothing really that nails it down. They keep talking about the electric dynamo with the circulating stuff in the inner core that is supposed to modify. And also, we're out of balance now. We're all lopsided in our orbit because again the central core is off axis, but why it actually flips, I don't know, John.
The theory of planetary dynamos is complicated and not terribly well understood.
That's science speak.
Part of the problem is that you'd really like to stick a magnetometer down in the core of the Earth and see what the field configuration down there is.
Except it's really hot.
Yes. There are, dimensional analysis arguments that seem to crudely predict the magnetic field intensities of planets and stars and things like that. But as to the details of how those fields arise and why they flip and all that, it's still very up in the air as far as I can tell.
Yeah.
I see nothing definitive.
Yeah, I'm just thinking, so, we believe in the conservation of angular momentum, right? So if the field is due to a circulating current of molten iron or something like that, it can't just change direction without something compensating for it. So then I wonder if, the crust of the Earth the day changes or something. Well, not the day, but anyway, it's very interesting.
There hasn't been a leap second in a while. For the most of the 20th century, the Earth was decelerating, and the Earth's crust was decelerating in its rotation, and it's been pretty stable for the last couple decades. So yeah, something is happening in the exchange of angular momentum between the various components of the Earth, and it's not terribly well understood what that is.
Well, we do know that the North Star, the North Pole, is shifting dramatically, and it's gone. It's closer to Greenland now.
Yeah, well, it's not the North Star. The magnetic North Pole is shifting very fast. Yes,
and it's going goofy.
Yep.
I don't know if I'd call it goofy, but it's.
I like the term. What's happening to the Earth's magnetic field? It's going goofy.
Right.
But the other thing is that it's not necessarily true that the direction of the circulation of the fluid needs to reverse in order for the direction of the magnetic field to reverse, because Maxwell's equations are symmetric. Yeah. If the dynamo can make a field pointing the way it is right now, the same dynamo should be able to make a field pointing the opposite way if the seed field is reversed.
It's just getting from this to that.
Yeah, exactly how that oscillation occurs, I don't think is well understood at all.
It's reminding me of an idea I had that I still think was a pretty neat idea when I was a teenage astronomer. And at those days, back in the 50s, people did not know about Venus's rotation, the Venus's day, because Venus was totally cloud covered. And my idea was, let's suppose that Venus has a magnetic field that's not aligned with its axis, and it has aurora. Maybe we could see an aurora in the clouds of Venus and see its rotation for that. And I actually mentioned this to an astronomer, Patrick Moore, and he said, well, maybe, but we haven't seen such aurora in Venus. So anyway, I thought it was a good idea, but didn't go anywhere, maybe. When did we, John, when did we start to understand Venus's rotation properly?
Oh, it was the late 60s that the radar astronomy work that Arecibo did. The lamented Arecibo telescope. Yeah.
So that could see features on Venus's surface through the atmosphere by radar, right? So,
that's right. That's right.
And see, eventually
we could measure the rotation rate, and it could sort of produce images, but because they were pulse Doppler radar images, and the velocities in the northern hemisphere were the same as the velocities in the southern hemisphere, it couldn't make an image that distinguished between north and south. So the northern hemisphere was juxtaposed on the southern hemisphere in these radar images.
So we sent powerful radar pulses to Venus.
Yes, using the Arecibo telescope. That's one of the things it was really good at.
Yeah, it also took similar sorts of radar images of asteroids and whatnot, if I remember correctly.
The other thing, Michael, is that that actually is related to how the differences between the different rotation systems in Jupiter were resolved, and it was understood what the rotation rate of the core of Jupiter is. It wasn't done directly with the aurorae, although those have been observed now, but in the 60s, what could be observed was radio emission from the magnetosphere. And that showed a period that was related to the rotation of the magnetic field, which wasn't the same as the rotation of any feature in the atmosphere like the Great Red Spot, although it was close, of course, because the features don't move around that fast. So that was how astronomers figured out the rotation rate of Jupiter.
Interestingly, also, the sun does not rotate as a solid body, right? The
That's right.
day is different in the equator as it is in the tropics or at other latitudes, right?
Right.
Yeah. So
And we don't really know what the rotation rate of the core is by terribly accurately, although the asteroseismologists, or I guess they're called helioseismologists when they're in the sun, have reasonably good estimates now.
Excellent. Well, go ahead.
I noticed that just the other day, they announced a breakthrough. Are we ready for the breakthrough?
All right.
That they were working with the laser methodology of creating a fusion, and it was a tremendous breakthrough. And then you actually read it, and it's 70%. So they only got to do another 30% and they'll break even. So although I had to chuckle at the breakthrough, it was a huge jump in technology.
It was a huge jump. They got 8 times the yield out of a shot that they'd ever gotten.
Ever before.
It was the difference between a big firecracker and a stick of dynamite.
Yeah.
Don't expect it to be powering our grids for a while, because I mean this is a shot, and it's not something you can do every second or even 10 times a second or something like that.
And the popular press was going, oh, we're on the verge of fusion power, and it's going to be what? And
it was a megajoule. The solar panels over my head make a megajoule about every 100 seconds when the sun's right on them.
Mm-hmm.
And another thing, I mean, I don't want to be pessimistic about this, but another thing is that every time you have this fusion event, you emit a lot of neutrons, which damage the whole apparatus, right? So we do not have materials that's going to withstand the radiation from a fusion reactor that's 100 megawatts or gigawatt or something like that. So
the best, as John says, the best sustainable fusion reactor and environmentally friendly is STAR, and we happen to have one pretty close.
Yeah, it's lovely.
Safe distance.
Right. All right. In the sake of time, let's, it may be that in the future we can come back to some of these topics about stellar fusion or the way it compares to Earth fusion and whatnot. That would be a rich topic for the future. But right now, I'd like to take us into the realm of relativity and Einstein's theory. So we're going to have a deep dive topic now presented by Ivan, who wants to talk to us about the twin paradox. Is that when you have twins and you weren't expecting it? What's the twin paradox, Ivan?
There could indeed be a paradox there, but that's not the one I'm going to talk about.
The other one.
This one is related to special relativity. So I'm going to, although we're calling this a deep dive, I'm going to try and do this without any equations whatsoever. And but relativity is one of those subjects that can be deep nonetheless. So, I'm going to talk about what motivated relativity, like why do we need it? Why did we need Einstein's relativity? I'll talk about what time dilation is, and then I'll describe the twin paradox and the resolution to the problem. So there are some general principles that we think are really important in physics, that the physics should be the same no matter how fast or in what direction you're moving, that we have some set of laws that we don't have to throw them out if we move to another galaxy, or if we're sitting on another star. We want the laws to be, the basic laws of physics to be the same. Of course, local conditions may be different, like it's really hot on the sun and they're not nearly as hot on the Earth. So there's different physics there, but we want that if you did happen to live on the sun and you looked at the Earth would still make just as much sense as someone who's on the Earth, right? So, and one of the most basic things is accounting for our motion in space. And physicists talk about something called the rest frame, which is how I measure things, how I perceive time and distance when I'm at rest, like when I'm, well, not when I'm at rest, but from my perspective. So when I see somebody else moving past me, they have their own reference frame in which they're at rest. So if someone is passing by on a boat, for example, then I see them moving at a certain velocity, and whatever formulas we have to describe our physics, when I look at them and they look at me, we're going to, or if we both look at some third experiment, we expect to see the same result and use the same laws of physics to calculate the answer. So what Einstein said is that, well, we can just sort of boost our reference frames. We'll just add velocity. And in Newtonian physics, velocities add intuitively, right? So if I'm on a boat and I throw a rock forward in the direction the boat's moving, then the rock flies at the velocity I threw it at plus the velocity of the boat, if we ignore air resistance. And that's what's intuitive in the everyday world. And of course, we can rotate among X, Y, and Z, and X, Y, and Z are different directions in space. They can rotate into each other. But time doesn't rotate. Time doesn't change. Time is the same for every observer. So why did this need to change? It needed to change because of what we learned about light. So Einstein's relativity postulate is the speed of light is a constant for all observers. So why did Einstein come up with this? Well, he didn't just pull it out of the ether. That's a little physics joke. Unlike sound waves, light waves exist without a medium. So if you have a volume of air, we can have sound waves moving in the air. But if I take all of that air and start moving it, so now the air is moving, and then there's a sound wave in the medium, the speed of the wave is the speed of the wave in the medium plus the speed of the medium. Well, it was once thought that light, I mean, just like all the other waves that we know, light is probably the same. There's a medium out there called the ether. We can't see it. We haven't been able to measure it, but maybe it's out there. But experiments showed at the end of the 19th century that we could find no trace of it. That we would think that the ether, if it was there, we'd see differences in the speed of the ether. You know, if we can't measure it in the lab, it must be something that's very permeable. So as the Earth goes through space, it will be passing through this ether in different directions, and we should be able to see differences in the speed of light when at different times in Earth's orbit around the sun. That didn't happen. And so for this and other reasons, we believed that light existed just as a sort of a property of the vacuum. The other thing is that Maxwell's equations that describe light waves say the speed of light is a constant scalar quantity. In other words, it doesn't differ from one frame to another. So if Maxwell's equations are correct, then we both share Maxwell's equations. And so we're both going to measure the speed of light to be the same thing. So this creates a problem when you start to try and add velocities to the speed of light. Also, causality would be weird if observers could travel faster than physical processes. You might be able to observe effects before their causes in strange fashion. So all of these things kind of came together, and a lot of these things predated Einstein's actual formulation of relativity, but he was the one that put it all together. So Einstein's relativity says the speed of light is a constant for all observers. And in order to make this happen, when we transform coordinates from one reference frame to another, the time dimension and the space dimensions intermix. And in order to make this so, a little bit like the way north and south and east and west intermix if you rotate your compass, the same thing can happen when you move from one frame to another that's moving relative to it. So this is a representation of what these transformations look like in Newtonian physics. So in Newtonian physics, if you have the Earth here, the Earth at rest, and you have a spaceship that's moving, and I have the space dimension in yellow and the time dimension in blue. And so the Earth stays where it is. It's at the same point in space, but just moves in time. And the ship is moving through space per unit time. So it's represented by this line. Well, in Newtonian physics, to go from the rest frame of the Earth to the rest frame of the spaceship, I'm just going to subtract the speed of the spaceship through space. So now the spaceship is at rest, and the Earth is moving at minus the speed of the spaceship. That's intuitive. But we can imagine what happens if the spaceship emits pulses of light. And if you use Newtonian space and time, then you end up trying to add the velocity of the spaceship to the speed of light or subtract it from the speed of light. And then you get into trouble because now you're violating Maxwell's equations. And of course, to fix that, what Einstein did is he said that the speed of light is a constant for all observers, and we're going to have to change the way we do transformations from one frame to another. So the solution is something called the Lorentz transformation. And in this transformation, what we do is we elongate or expand or dilate time, and we compress or contract space. And when we do this, we end up preserving the speed of light for all the observers. So to talk about this, I'm going to talk first about clocks. And this is the way special relativity is the form of relativity that we use when, like this, it's the special case where there's no acceleration. So what we want is we want a clock that depends in some, that's based on some simple physical principle that doesn't depend so much on, let's say, the speed of an object bouncing around inside a case. So the easiest way to do this is to have a couple of mirrors and have a light beam bouncing between them. And we imagine that this is our clock, and that one tick is the light beam moving, between, from one mirror to the other. And so then if the mirrors are a meter apart, then each tick is 1 divided by 299,792,458 of a second. So here I am at rest with my clock, and I'm watching my clock tick. And now we're going to imagine what happens when we have another clock that's flying by my own. So here's my mirrors of my other clock, and this clock is moving. And as it moves, the light beam is going to reflect from one mirror to the other and then back to the original mirror. There we go. So what you'll see is that, you know, the speed of light is a constant, but the light has had to travel a longer distance from the perspective of the person that's at rest. So this means that time for the moving, relative to this clock is actually running slower because the light has to travel further between the two mirrors. So once we have time dilation, there is a formula for it, and all physics students learn these formulas. And we often apply them in very, like, for example, when I was a graduate student, we did an experiment where we were measuring the muon lifetime. So muons are created in cosmic rays, but they only live for an average of 2.2 microseconds. And at that speed, at the speed that they're moving, which is very close to the speed of light, come through the atmosphere, they will actually have decayed before they hit the surface if there were no relativity. But because of relativity, their clocks are running slower, their physical processes are running slower. And that means that they actually reach the surface of the Earth. And so you can do the calculations and see, you know, how will these muons survive to the Earth's surface? And they do. But even though we have equations for special relativity, it's still difficult to understand. And the twin paradox is an example of something. It's really a way of exposing a misunderstanding or a faulty assumption. So, and this is true of paradoxes in general. When somebody says there's a paradox, they really mean, hey, look, we think we understand this, but if we do understand it, it leads to this seemingly contradictory position. So then, you know, paradoxes are puzzles to be solved. And this one has a solution. So what is the paradox? Well, the paradox is that you imagine a journey, twins. You have one twin remains on Earth while another twin gets in a spaceship, flies, let's say, to the nearest star 4 light years away, and then turns the ship around and then flies home again. And this ship travels at almost the speed of light, or a significant fraction of the speed of light. So for from the point of view of the observer on the Earth, he sees his twin fly off in the spaceship, redshifted, and then sees the twin flying home. And since the ship is moving, and this, you know, in his rest frame, the twin on Earth, that person's rest frame, because the other twin is moving, the other twin's clocks are slowed down. So while, let's say, you know, 10 years have passed on Earth, this astronaut, the twin astronaut, if they moved fast enough, would have aged hardly at all. So the twin on Earth would be older. But the paradox is, what if you instead said, okay, I now am going to be the twin that instead of staying on Earth, stays on the rocket ship, and the twin on the rocket ship sees the entire universe, including the twin on Earth, fly away at almost the speed of light, and then sees the entire universe turn around again, and then the Earth fly back at him at almost the speed of light. So in this case, the twin that's sitting on the spaceship sees the clock of the rest of the universe slow down. So he would say that, well, no, I'm going to be older than the other twin because the other twin was moving. And so just to explain, like, why the clock is slowing down, this is just another sort of diagram of the time dilation, you imagine the twin on Earth has these two mirrors and the light beam bouncing between them. During the, it's going to get, this clock is going to be ticking billions of times, a minute. And if the astronaut was moving fast enough, it's possible that there would only be 1 or 2 ticks before he got to the destination, and then 1 or 2 ticks before he got home. And this is the speed of physical processes. So it means that almost nothing physical has happened to this astronaut during the whole journey. And that's why the twin on Earth has experienced all these physical processes, including the aging, whereas the astronaut has not. That's what time dilation would tell us. So the false premise of the paradox is that, this is one depiction of the journey, is that, in the Earth's frame, you see the twin depart and then return. Well, the false premise is that we can kind of split this journey into a different set of frames where the outbound astronaut frame is the same as the inbound astronaut frame of reference, and the Earth instead has changed direction. And the problem with that is that these two frames are not the same. They're different frames. That if you are the astronaut and you say, okay, I'm going to plot everything out from the point of view of this astronaut, then he's saying, well, I'm at rest right now, but in order to catch up with the Earth, in order to meet with the Earth, I'm going to have to actually change direction by twice this speed to be able to catch up with it. So in other words, if you pick the first frame, you pick the astronaut's outbound frame as the primary one in this rest frame, then this astronaut does see the Earth fly away and does see the clocks on Earth slow down. But then there's a third frame here, which is the astronaut now has to fly to catch up with the Earth. And in order to do that, it has to go even faster than the Earth. So clocks are slowed down even more on this frame than they are for the person that remains on Earth. And you can do it with the other frame too. If you take the last frame of take the return journey as your rest frame, then it's like, oh, I'm just waiting here for the Earth to show up. But then when you put in the consistency that, hey, but how did I get here ahead of the Earth? Just waiting for it to show up. Well, I had to fly faster than the Earth in order to get into this position. And so when you account for the frames correctly, then it resolves the paradox that no matter which way you calculate it, you will find that the twin that remains on Earth is older. Now, when I was a graduate student, we were never actually asked to calculate, to do this whole calculation from beginning to end. We were told about the paradox and told that, that it's not a problem. But when I was taught this, we were never given the problem to do. And I remember, I don't know where I got the idea, but it seemed to be, oh, this problem is resolved by the general theory of relativity, and it has to do with the acceleration that the astronaut goes through, that the person on Earth does not. It does have to do with the fact that these two frames are different, but and you can calculate that the acceleration will have some effect on the relative age of the two twins, but you don't need general relativity to have this effect. Just special relativity alone will account for this. So that is the twin paradox and the resolution to it. And like I say, in physics, when in school, we were given the equations, we derived the equations, we would apply them in specific cases. But when I had to actually account for this and like work it out, I'm like, wait a minute, this doesn't work. I had to really think about this. So the bottom line is that when you're trying to solve these relativity questions, if you think about these clocks and the mirrors and think about the path that light has to take, the light bouncing between the mirrors is just a proxy for pretty much every physical process. So if you think about it in those terms and remember that the speed of light is the same for all observers, you can usually resolve these things in an intuitive way, but it's not easy.
Thank you, Ivan. Is that the end of your formal presentation of the topic?
Yes.
All right. So you say that it's the answer can be fairly straightforward as long as you keep your frames of reference and your sort of space-time geometry in proper consideration. But
I mean, yeah, straightforward, but
not intuitive.
But not intuitive, right?
Right. Yeah, relativity is very counterintuitive, I think. You also mentioned Maxwell's equations. Is those of you who are well versed in the history of science, if I remember correctly, Einstein came at his theory of relativity by thinking about the implications of Maxwell's equations. And
yes, the example he gave in his original paper on special relativity was, if I have a magnet and I have a coil of wire, if I move a magnet like this, I see a voltage induced in the coil of wire. If I move the coil of wire like this, I see the same voltage. But that is a puzzle, because if you try to interpret Maxwell's equations in a Newtonian geometry, you don't get that. These are two different effects in Maxwell's equation. In one case, you induce an electric field, and that causes the voltage in the coil. And in the other case, the motion of the electrons in the coil pushes them around due to their interaction with the magnetic field. And the fact that that effect follows the relativity principle is a puzzle in the context of Maxwell's equations.
Without relativity.
Well, what he did was he showed that if you postulate that the speed of light is the same for all observers, then this effect makes sense.
That's one of the things you said in your example, Ivan, was that when the rocket ship is moving away from you, an observer on Earth would observe a clock on that rocket ship moving more slowly. But you also said when the rocket ship is coming toward you, the clock still moves more slowly. And if I'm just trying to use naive intuition, analogous to red shift and blue shift, with the Doppler effect, how when something's moving away, it goes, whereas it's coming towards you, it goes, upper, higher frequency. It might seem intuitively to people that if something's moving toward you, you'd see its clock ticking faster, but that's not what happens, right?
Well, the question is what you infer versus what you see. You do see it blue shifted when it approaches you. But then if you correct for the blue shift by looking at its velocity, what you then infer is that the clock is running slower than its rest rate.
It's like
here we haven't done it with people in rocket ships, but we've done it with precision clocks, right? We've sent precision clocks around the Earth in airplanes. I presume it's been done in satellites as well. Yes. And then brought them back to Earth and compared them with the identical clock that was kept at rest in the laboratory, and shown that there is indeed a time difference between them.
Yeah, it was done 50 years ago. Now, to do that experiment, what you have to do though is you have to do it twice. You have to fly the clocks around the Earth to the east, and then you have to fly them to the west, because there are two things going on. There's a special relativity time dilation, but there's also the general relativity gravitational redshift, because planes don't fly on the surface of the Earth. And by doing the experiment twice, one going east and one going west, you can separate out the two effects.
Okay. And general relativity tells you also that when the clock goes higher up in the outside to low gravity, then it speeds up, right?
That's right.
GPS only works because you correct for that effect.
That's correct.
We've also done this with, Ivan mentioned muons, which have a lifetime of about 2 microseconds, right? Now at Fermilab, we have this famous experiment storing a beam of muons in a ring, and they're going round and round this ring at about 10, they've got energy about 10 times their rest mass, they're going so fast. And they live for much, much longer than the 2.2 microseconds. So you can imagine if we created a muon at high speed and one at rest at the same time, the one at rest would die, while the one at high speed is still going round and round and round and decaying away with a lifetime that exactly reproduces what relativity tells us. That's another test. Very good.
Yeah, I've got a question for you, John, that occurred to me. You were talking earlier about looking at neutron stars that are pulsars that emit, like a radio beacon. It occurs to me that because of the time dilation effect of relativity, both with the speed at which that beam is moving around in space, as well as the gravitational redshift that clocks slow down in stronger gravitational fields, maybe if somehow I could sit beside this radiating hotspot on a neutron star and time the interval in between. Well, I guess it wouldn't be flashing if I were sitting beside it, but if I were very, very near it, if I were hovering, up, 1 meter above the surface of this neutron star and timing when that flash came by me, would the interval between flashes be more rapid than it appears to be from us outside of the gravity well of that and the high rotation speed of that?
We think so. We don't have a good way to do the experiment, but we think so.
Huh, that's cool.
It's a good guess.
Well, for white dwarfs, you can do it because you can see the gravitational redshift of the spectral lines.
Yeah.
Mm. Yeah, there are atoms in a white dwarf, but it's just
they're atoms on the surface. Well, they're atoms on the surface of a neutron star, but they're so ionized that you really don't see that the ionization state is so hot that you really don't see a spectral line. And most of the interesting spectral lines come from heavy elements, and those get gravitationally separated from the surface so fast that you just don't see them on a neutron star. But we do see heavy elements on the surfaces of white dwarfs, and we do see the gravitational redshift. Yes.
I'd like to ask Ivan a question inspired by his diagram. You showed 2 diagrams, one in which the Earth is stationary and the spaceship is shooting off very high speed and then turns around and comes back. The other diagram, you showed the spaceship at rest, the Earth shooting off at very high speed, turning around and coming back. Now, we know about conservation of momentum. The change of momentum of an Earth traveling at nearly the speed of light and turning around and coming back, it can't work, right? There's something wacky. It doesn't mean
this isn't a dynamic argument, it's a kinematic argument.
Relativity doesn't
use the technical terms.
It's a coordinate change, right? It's a change of coordinate system, like you're changing the rest frame. Let me find the slide. Hang on.
Conservation of momentum doesn't come into the argument because you're assuming some external momentum sink that takes account of that in this. You have to assume its existence just to make the spaceship move near the speed of light.
No, but I'm a practical person, and I think I can imagine the spaceship turning around and coming back to Earth by emitting out, jets, but I can't imagine the Earth turning around and changing its direction.
But from the astronaut's point of view, that's what's happening.
Just put a really big impossible laser on the Earth and use it to thrust the Earth around,
And again,
but it's really just, it's really a question of like what rest frame, like, in other words, if you look at the ship flying away from the Earth, right? What we want to do is we want to say, well, from the point of view of the person on the ship, how does this look? And it's true that the ship is going to have to expend energy to move in another direction, but whether there's an engine on the ship or whether there's some other force which is going to move the entire universe in the opposite direction.
As I think of it, the idea that one frame is as good as another is not correct. What I see is in your spaceship, you have a laboratory with no windows, it's just a laboratory. You can do any experiments you want in the laboratory. As long as the ship is not being accelerated or decelerated, but just going free fall, at same speed, then all the experiments you do are exactly the same as the experiments of somebody else in another spaceship in a different, forgetting about gravity for the moment, because that's an acceleration. It doesn't mean that the spaceship's rest frame or the spaceman's rest frame is as good as any other rest frame, because you think that the whole universe is shooting off. All the stars are being given a motion of nearly the speed of light in some direction. It doesn't make sense to me.
Well, there is a cosmological frame of reference.
There
which
is
the frame in which the cosmic background radiation looks at the closest thing to uniform temperature all the way around the sky.
Right.
And that is an interesting thing, but that has to do with the history of the matter and energy in the universe, and not with the rules that govern their dynamics.
Right, and we are moving through that frame, so we don't see the microwave background as uniform in all directions because we're moving through it. However, I do think relativity says that the physics in a closed box in a free fall is the same no matter what velocity you have. Okay, it's irrelevant, but that doesn't mean to say that it's okay to think of the spaceship as being at rest and the universe is shooting up, all the stars going off at 0.9 C or something in one direction.
But it's a bit more than that, right? It's like I need to be able to see into the other ship and look at the experiment from my perspective and say, that makes sense to me, right? Like I'm observing that experiment. I've got to see the same result. And then I've got to say, like, yes, this experiment turned out the same way, but these quantities may be different just because of my frame of reference, but it all lines up. So it's not just within my ship. I have to be able to look at somebody else's situation and say, oh yeah, that guy over there, yes, from my perspective, this may look bigger or smaller or slower or faster, but it's basically the same physics. And there's a reciprocal relationship, right, where they would look at me and see the same thing. So it's the Lorentz transformation that's connecting those things. So I'm going to look at the other frame and say, yeah, if that was happening here, and then I transform it into the other frame, it would be the same.
There's nothing in the mathematics or even the conceptual ideas that describe special relativity in some circumstances, such as this one. There's nothing that requires you to take into account how the motion arises. It could be a rocket, it could be a solar sail, it could be something shot out of a cannon at 0.9 C, etc. All of the cannon. Yeah, heck of a cannon. All of those practical considerations about how a particular frame of reference became separated from some other frame of reference, all of those are irrelevant. It's just the core notion that if you are in uniform motion, there is no physics experiment you can do to distinguish the fact that you're in motion versus something else is in motion relative to you. Now, there are common sense things like the conservation of momentum for the universe and whatnot, but that's why you look at a closed box, you know, where you're not receiving signals from the Andromeda galaxy racing away from you and whatnot. It's just, it's locally irrelevant which frame of reference is in motion with respect to another one. In fact, either of them could be considered in motion with respect to the other, and all the laws of physics still work.
Well, if I keep thinking back to the early days of the space program, when we were, everyone was watching the Saturn V's taking off, and you'd sit there and you'd watch the gantry, and you'd see this enormous rocket ship taking off and picking up speed and going up and up and up, and you go, wow! And then you'd have a picture from inside the capsule as the Earth is receding away from them.
That's true. Yeah.
And so, two perfect examples of just a frame of reference. The exact same thing was occurring, but from the astronaut's point of view, the Earth was receding. From my point of view, watching it go, it's the rocket ship is going up. So it's the same thing, but different.
So some of the people who witnessed those in person quipped that it felt like Florida was going down.
Oh, yes.
Wow.
The noise, the intensity of that pressure wave.
I could see that for the first few hundred feet or so, you're concentrating. You know, it's like being in traffic. Sometimes you don't know if you're moving or if the car next to you is moving.
And the corollary to all this is, by the way, that Emmy Noether, a mathematician, showed that the fact that in a laboratory, any laboratory in free fall, no matter what direction or speed it's going in, is in free fall, the physics is the same, implies a conservation of momentum. And the fact that it didn't matter which orientation it has implies the conservation of angular momentum. And the fact that it doesn't matter what time it happens, it can be done today or next week or the week after, other things being equal, implies energy conservation. So she tied these energy to time, orientation to angular momentum, and speed to momentum.
And by she, who are you referring to?
Emmy Noether, Noether. She was a brilliant mathematical physicist, or mathematician, really, but she did that. And Einstein said she was the most brilliant female physicist of the century. But,
so yeah, it's interesting, right? Like if the universe begins at a single event, you no longer have time translation symmetry at that point, so you don't need to conserve energy.
Yeah, that's right. That's right. I think that's right.
Fascinating. And very counterintuitive.
This whole thing has been, hello.
Yeah, relativity is, I mean, some of the equations that that I learned as an undergraduate, and the other physicists I'm sure did as well. The equations are pretty easy to write down. They're just algebra, you know, a squared, b squared, c squared, etc. And it's sort of trigonometric.
Yeah, that was Minkowski's
right.
Contribution, was that he noticed the equations that of the Lorentz transform that Einstein had independently maybe derived were rotations in a geometry with a very odd metric. In fact, the Minkowski metric doesn't satisfy the official mathematical definition of a metric because it has a negative signature. But be that as it may, it turns out it's a perfectly good metric, and it seems to describe reality rather well.
You've got your A and B and C. You're reminding me of a great cartoon showing Einstein at a blackboard, and he writes E is ma squared, crosses it out. Then writes E is mb squared, crosses it out. E is mc squared. Yeah. Well, that's it. Okay. Yes, you got it.
I've got all kinds of stuff around me here.
Yep.
Of course, that equation, by the way, which is so famous, but it's only true for an object at rest. Once an object is moving and has momentum, that equation is not correct.
Correct. Yeah.
Well, you're, the old school, we talked about relativistic mass, and And that, the old school stuff worked okay.
It works okay.
No, you can't keep M constant then. You have to change M all the time.
You have
So
to change M all the time. That's right.
Well, Ivan, in your presentation, you talked about light bouncing between some mirrors. And you said that if you're in the spaceship and you've got this sort of light clock that's bouncing around, it looks normal to you. The light just goes up and down from fixed spots in your spaceship, floor to ceiling, back and forth. But if you observe it from the Earth, you said that the light has to go a longer distance to get up to the ceiling and then back down to the floor. I'm doing this in reversed in a camera so that it looks okay. But this triangle shape, it goes up to the ceiling and then back down to the floor, and that's a longer distance for somebody on Earth. How do you reconcile the fact that the light traveled further? How do you come up with a velocity that's the same? If Einstein says the velocity is the same for all observers, how do you do that if it traveled further? You don't. This is time dilation. Well, it travels farther and it takes longer to get from one mirror to another. Right, and that's the answer I'm trying to tease out, is that the only possible way that a longer path can represent the same travel speed is if time also changes. You can't just have one thing, only the distance changing or only the time changing. They both have to change in order to give you a constant velocity. And that's what I was trying to get at.
So the story goes that Einstein as a boy wondered what would happen if you could catch up with the speed of light and even with a light beam and even overtake it. And that's an interesting story. And now physicists are wondering, with neutrinos we now know have a little mass, but the mass is so small compared with the energy that they travel at essentially the speed of light, but not quite. So you can imagine actually overtaking a neutrino. And then, now, does it turn into an antineutrino or not? And that is a big question right now. And we're talking about two types of neutrinos, Dirac or Majorana neutrinos. One type would turn into an antineutrino when you overtake it. Not a practical thing to do because they're going at enormous speed, but so we're trying to, but there are experiments that can tell the difference between these.
Mike, has there been an experiment? I mean, we all who are steeped in the theory, at least of special relativity, we all just presume prima facie that a neutrino having a tiny bit of mass cannot possibly go at the speed of light. Have there been practical experiments done to prove that neutrinos do not go at the speed of light?
Well, that's an interesting, because there have been some measurements over long distances to try to measure the speed of neutrinos. And indeed, there was a big hype about a measurement apparently from CERN, neutrinos created at CERN, going to Italy to a tunnel under not far from Rome and so on, and being detected there. And the neutrinos were pulsed at origin. And some of the experimenters said, wow, these seem to be coming faster than the speed of light. Wow, and they actually stepped out of line and started talking to the press about this. And their colleagues were horrified and said, look, we still got to check all sorts of things, And in fact, where they did check all sorts of things, they did find that they had a problem, actually, a hardware problem.
Yeah.
And in fact, they don't travel. But it has been others have suggested that maybe neutrinos do travel faster than the speed of light, but there's no evidence that they do. And
also no evidence that they travel slower. The mass is so tiny that at the energies we can make neutrinos.
That's right. But
Fermilab's got a huge amount of work being done right now with neutrinos. Do we have any evidence coming from that source?
Well, there have been, let's see, there has been, yes, I think there has been a result quoted for the speed of light from neutrinos from Fermilab to northern Minnesota. And it's consistent with the speed of light because the masses of the neutrinos are so small compared with their energy. the difference from the speed of light is not detectable yet. You know, it would have to be more. You know, it's outside the limits of what we can do.
It's a really short distance from here to Minnesota, really.
Right.
Well, you know, you
but-
have to measure. The problem is that you have to measure the time of origin of the neutrino, and they come first. That's smeared out because they come from the decay of particles, muons or pions, and they're spread out in time. And then your detector has a time resolution, which is not a picosecond. You know, it may be a nanosecond or something like that for their detectors. So you know, we don't have that. It would be interesting to try and do better and better and better with that, but the neutrino masses we know are very, very small.
I
indeed-
forget whether the limits you can do astrophysically are better, but I do note that supernova 1987A in the Large Magellanic Cloud emitted a pulse of neutrinos that was detected on Earth a few hours before the light of the supernova. But that implies that the light, this thing is, you know, 500,000 light years away. So this implies that the light and the neutrinos traveled at almost the same distance. We do.
How is it that the neutrinos arrive before the light?
Well, because the neutrinos tell you when the core collapsed, and it takes a while for the envelope to notice
The rest of the star.
the rest of the star.
Yeah.
You have to somehow, you know, a star is a big thing. It takes a while for the events, even as violent as a supernova, to propagate from the core of the star out and start blowing the envelope off. And then you don't really see the envelope blow off until it's expanded substantially.
And here is a really interesting food for thought for everybody, which is that, you know, we know 3 types of neutrino, one associated with the electron, one with a muon, and one with a tau, which is a heavier version. But we know that these don't have perfect masses. There are 3 different masses, M1, M2, and M3. And there's a mixing between these two. So each type of neutrino, the electron type, is a mixture of the 3 masses. And conversely, each mass type is a mixture of the 3. And it's really mind-bending and very, very interesting. And this is what people are really studying now, because we know these 3 neutrinos have different masses. But is it too heavy and one light, or is it the other way around? And so on. What are these masses? And that's really a focus of the research at Fermilab and also in Japan now, trying to understand these masses.
This for decades was a puzzle in astrophysics. It was the solar neutrino problem, where neutrinos, you can detect neutrinos coming from the nuclear reactions in the core of the sun. And the rate at which you detect these neutrinos is 1/3 of the rate that you infer they're emitted from the known luminosity of the sun. Because
that's a very curious number. 1/3 is a very curious number.
Yes. Well,
Yeah.
it's a very curious number, but you know, it took decades, literally, to figure out that it was this mixing that was causing it. Because by the time that let's see, are they antineutrinos? I forget. By the time the electron neutrinos reach the Earth, they have mixed thoroughly, and 2/3 of them are the other kinds.
And there was a final experiment at Snow, which is in Canada, which detected measured once the electron type of neutrino, and then they did another measurement that measured the total number of neutrinos of all types, and they found that they got this factor of about 3. It's not exactly 3 actually, but that's a detail. It's about 3.
Bringing this back to E equals mc squared.
Yeah.
Right. When a neutrino, when we're detecting neutrinos, you know, a neutrino comes into the experiment. Let's say it's an electron neutrino. It needs to have enough energy to make an anti-electron, or if it's an antineutrino, has to preserve the electron number. So if it's an electron neutrino, it has to create an electron. There we go. And so if the neutrinos don't have enough energy, then they can't create mass, right? You can create mass from energy by E equals mc squared. This is a very heavily oversimplified statement about what goes on. But the reason that, if electron neutrinos are created in the sun, and then they mix with tau and muon neutrinos, but those neutrinos don't have enough energy in them to make the heavier mu's and taus, they won't show up in our experiments.
They do if they can still scatter. They can still scatter on a nucleus. They can't make taus or mu's. So they become sort of sterile in that sense, right?
Does that mean like the low energy neutrinos left over, presumably from the hot phase of the Big Bang, they're redshifted like the cosmic microwave background? They're redshifted to such low energies that they won't be able to activate these detectors we have.
We have no way to detect those.
Right. Well, no known way right now, John. But I mean, this is a big challenge. If you can detect the neutrinos that came from the Big Bang that are now have got a temperature, if you like, of about 1 or 2 degrees absolute. If you could detect those, that's perhaps a Nobel Prize for you, because that's a really hard problem. But they must be there. They should be there, and it would be very interesting to measure them.
Ivan, I wanted to bring this back to the notion of time dilation and the twin paradox. One of the nice little factoids I enjoy pointing out to people occasionally, there's this misconception in popular science and even in some science fiction that the limited human lifespan means that we can never get very far into the cosmos. For example, going to the nearest star would take almost 4 years, or a little more than 4 years, going at even the speed of light, much less, 70% or 80%. And one of the things I like pointing out to people is that because of the benefits of time dilation, in principle, doing away with technicalities and the engineering problems of sufficiently powerful rocket ship drive and all of that, just doing away with all of the engineering problems. In principle, you could get from here to the Andromeda galaxy, that's 2 million light years away, within the duration of a normal human lifetime, thanks to time dilation, as long as you move fast enough. Is that something
right.
Yes, it would have to be about 10 nines the speed of light, right, to do that. I mean,
right, but assuming that we have the magical drive necessary to get to those speeds, we can get there in kind of as little time as we like, right? Like we can get to Andromeda in an afternoon from our perspective.
On the rocket ship.
On the rocket ship.
Spaceship.
Now the people on Earth would get tired of watching
the
us.
acceleration will squash you, though. I mean,
the acceleration.
A minor engineering problem.
Yes, and never mind the amount of energy we need. Or as Mike was saying, on the AHA show, that getting this amount of energy, even if you get it from antimatter, that of course you can buy at any supermarket. But in principle, yes, right. I remember when I was a kid and reading about this and being like, oh, good, I'm glad that okay, I'll have to leave all my friends behind. I'll never see them again. But at least I can go and visit the Crab Nebula or something, and within my lifetime. It's not a very hospitable place or anything, but it might be pretty, right?
Yeah. So a couple of weeks ago, I had a lunch with a guy called Professor Francis Halsey, who is senior project investigator for the Ice Cube project in Antarctica. And they've measured the highest energy neutrino from the cosmos. And it's incredible energy, and it's come from, I don't know, God knows how many thousands of millions of light years away. I said to him, how much time has that neutrino experienced on his trip from distant galaxy? And he said, well, it's about half an hour.
Wow.
Wow.
And light beam, you know, to take that literally to its extreme, to its physical extreme, a light beam from a distant galaxy, you know, 12 billion light years away, that light beam, if you can somehow ascribe the notion of a duration to it, how long in that light frame of reference, how long did it take for that photon to journey from a distant galaxy to Earth? The time is zero.
Zero time, yeah.
Experience no time.
So every photon that by definition moves at the speed of light, there's no concept of duration. There's no concept of the passage of time. And yet we see photons that hit detectors and disappear, and other photons that miss the detector and persist. So if there's no concept of duration, how can there be concepts of different events happening at different times? I haven't figured that one out.
Oh, that happens in our frame, not the photon's frame.
No, the photons rest. You're right. I mean, the proper time of the photon is zero. Now what happens if the photon happens to go through a glass and to get slowed down?
Yeah.
Yeah.
Because of think about it.
And then a chemist sits there and goes, aha, a carbon-hydrogen band.
Something absorbed a little bit of that light. Right. Yeah. Well, I think it's true that even in a material, light moves at the speed of light. It's just constantly absorbed and re-emitted by electrons in the material. So when the light goes through, let's say, a thickness of glass, a given photon goes, oh, stop. Oh, here I go again. Oh, stop. Oh, here I go again. And that's the reason that light is perceived in bulk to slow down in materials, is because it's being absorbed and re-emitted, you know, trillions of times as it traverses a material. But
isn't that the concept of the ether?
no,
Well, we come back there again.
Well, if it's propagating in a medium, there is a medium, and it's not a.
No, but what you said, Scott, is reminiscent of one particular analogy for the Higgs mechanism, where the Higgs gives mass to particles. So you say the Higgs field is a field that fills the vacuum, and an electron going through the vacuum is actually going at the speed of light, but it keeps getting kicked backwards and forwards and backwards and forwards and backwards and forwards by this Higgs field. And that makes it go slower than the speed of light. And yet, if you could look at it on a really zoomed in timescale, you'd see that it's a zigzag path, but it's always going at the speed of light. Now, this is, I'm talking, and the same thing for other particles. The heavier particles get knocked backwards and forwards more, and therefore they go slower down. But I like that. I know it's an analogy, it's a sort of picture, but I quite like that picture. Because if you turn the Higgs field down to zero, the masses of electrons and other particles, like quarks, would go to zero. And they all go at the speed of light. So it sort of is a nice little intuitive sort of picture. Now, theorists will say, oh, it's more complicated than that, but I don't care what they say.
I think another question, which has always bugged me when learning about, you know, muons and, you know, that the duration of the lifespan of a neuron, it's not a neuron, a muon changing. You know, I don't want to get too far afield with this question, but there are some considerations from quantum mechanics that leads us to a very plausible certainty that there's no structure inside of things like electrons, right? There's no gears turning, there's no magnetic drive twirling around or anything. So what is it in a particle like a muon or even a neutron? What is it that keeps track of local time? How does that happen for something as fundamental as a particle? How does duration, you know, I know that there's this idea of half-lives, and a given muon could last natively in its own rest frame for a second if it lived if it was lucky enough to extend many half-lives. But what is it that keeps track of time in the rest frame of a particle?
It's a wave, and it has a frequency. if you look at the wave function is spinning around with a complex amplitude, and the rate at which that wave function oscillates is proportional through Planck's constant to the mass energy of the muon. And so it as a wave does have an inbuilt clock.
So John, how does it know when to decay?
That reflects the coupling constants to the other fields, you know.
So, I mean,
Right.
so one of the interesting things about the experiment, like the muon capture experiment that we did in graduate school, is, you know, these muons come down through the atmosphere and they end up getting trapped in our scintillator, right, which is in the dark. We have photosensors. So when it decays, we see a little flash and it goes through, and we can time. We know when it passed through into the trap. And then we also know, after it's been sitting there, how long it takes to decay. And of course, we get some distribution of, you know, what the average, and we calculate what the average life. Now, remember, it's already come down from the atmosphere above. It's been around for a while, right? So you might think that it would normally be 2.2 microseconds, but we've got to subtract some time, right? We've got to subtract a second just to account for all the time it's spent coming down through the atmosphere. That's not true. The average time you measure since after it gets to the trap is 2.2 microseconds, which is suggestive that it isn't tracking time at all. Right? It's just a certain probability of a decay per second
in a particular interval of time.
Yes.
That's true.
Yeah, there's another.
Merci, Monsieur Poisson.
There's another view.
Yes.
The following. So the muon doesn't do nothing. If you look at a muon on a very short time scale, which means a very uncertain energy by the uncertainty principle, it can become a W boson and a muon neutrino for a tiny fraction of time. And it's got to go back. It's got to go back because over a longer time interval, the energy must go back to the muon mass. But it's fluctuating. And the same with an electron. It can turn into a W boson and an electron neutrino for a tiny. Now the time is so small because the W boson is so heavy. It really can't. But this internal, if you like, I mean, one can draw the diagrams, and these are Feynman diagrams that shows an electron line with it turning into a W and a neutrino, okay, and so on. So these Feynman diagrams can be calculated. Now, and so what you put in is the masses of the W and the coupling at the vertices and so on. Now, when it comes to the neutron's an interesting one too, because neutrons have a lifetime of order sort of 14, 15 minutes or something like that. What happens? I mean, it's also time dilated if it's moving fast. But one way of thinking about it is you've got the quarks rattling around inside the neutron. There's two down quarks and one up quark, and they're basically point-like. But when they get really, really close together, an up quark and a down quark, an up quark can decay to a down quark plus a W, but then it's got to go back to where it was before because of energy conservation on a longer term. Now, okay, this is maybe a whole story about that, but we can't calculate the neutron lifetime from first principles, but I think of it like, you know, a quark has to decay, and to decay, the quark has to decay. An up quark can decay to a down quark by emitting a W plus boson, but it has to reabsorb it. But the W plus boson can decay to an electron and neutrino. That's how a neutron would decay. Neutron decays to proton plus electron and neutrino. How that happens on a tiny scale, when you zoom in, you see that the down quark emits a W plus and becomes an up quark, and the W plus. But it's not a real W because obviously there's not enough mass to make a real W, which means that you have to borrow energy from the uncertainty principle, and that happens over a tiny, tiny time scale.
That's how the W particle is related. It's one of the force carriers for what's called the weak nuclear force. And what Mike was just describing is the reason why in most circumstances, the most relevant feature of the weak nuclear force that people consider the most relevant feature is transforming one sort of particle into another sort of particle. But it is also capable of acting like a force. But that takes us pretty much to the end of today's allotted time. One of the things I'll add in just as a quick aside is that every one of the forces of nature has been constructed in a theoretical framework that is consistent with time dilation and length contraction and other effects of special relativity. Our best theory in all of physics actually takes deep accounting of the effects of special relativity, as Ivan has described them to us today. So without considering those special relativity time dilations and whatnot, without considering those, you do not have a mechanism to explain all of the observed forces of nature, including the force of gravity, electromagnetism, and the strong and weak force. So Einstein's special theory of relativity is enmeshed so deeply into the laws of nature that you really can't consider anything in detail without thinking about it. And it's hard to do. It's not very intuitive.
Degeneracy pressure.
Right. That's right. All right. Thank you all for joining us. It was delightful to have this conversation today. We'll be back in a couple of weeks. And Mike, I think you'll be up for choosing a topic in a couple of weeks. And we'll see what that is. Check us out on meetup.com. Look for the Prairie State Humanists to get advanced warning of when and what our topic will be. Take care, everyone. Those of you who are watching live or on the recording, give us a thumbs up, leave a comment, let your friends know if you think that this is a helpful and informative and entertaining science program. Take care, everyone.
See you guys.
Bye.
Be well.